Kabir, and I'm a recent master's graduate from Ulster University. So today I'll be presenting a paper on the implementation of a university chatbot using LLM and a RAG-based approach. So the chatbot uses AI techniques, including large language model and a method called retrieval augmented generation, which is RAG for short. So starting with what RAG and LLM is. So I know RAG sounds like something you would use to clean your keyboard, but that's not what we're talking about. So RAG stands for Retrieval Augmented Generation, which is a system that fetches relevant data to answer questions. So while LLM stands for a large language model, which is an AI model that can understand and then generate human language. For example, the likes of ChatGPT. So the reason why we undertook this research is because we want to like reduce the over reliance of hello? I hope you're with me.
So yes, we can still hear you.
Okay, good. So the reason why we undertook this research is because we want to kind of like reduce the over reliance of universities in information dissemination methods like phone calls, website browsing, and emails. Now, of course, these methods are effective to a certain degree, but there are challenges. So, for example, there are times that you'd get a delayed response for a query that is supposed to be a simple question for an administrative staff, or maybe it could be situations that would warrant repetitive inquiries. So another thing is it could be situations where it would seem like you need a GPS just to navigate the university's website. So, and that is where this RAG chatbot comes in. So with RAG, what we're trying to do is that we want a chatbot to look up relevant information in real time from a database and then combining with the AI model's language ability in order for you to be able to give a useful response. So the primary objective is we want to develop a chatbot that is quite adaptive. I mean, chatbot that can actually adapt to real-time situations in terms of knowledge, in terms of dynamic knowledge. You understand? So we want to develop a chatbot that it is available 24/7 in the sense that you do not need a human to be available before the chatbot can give you a response or anything like that. So and the chatbot, I mean, the questions can come in the form of simple questions like what's the tuition fee for MSc course, or it can come in form of complex questions, and the chatbot would be able to respond accurately. So then another thing is that we want to explore the limitations of large language models itself. So talking about the architectural design of the chatbot, the architectural design starts with a data set from the Faculty of Computing, Engineering, and the Built Environment at Ulster University. So you can think of the data set as a big library full of books or documents that contains all the knowledge that the chatbot would use to respond. Now, the next thing is that we want to make chunks out of this document. So, for example, when you have a big book, for example, you want to read the entire book you don't want to read the entire book every time. Let's say, for example, you need a piece of information, or so. And when you want to get that piece of information, you don't have to read the entire book. You simply break it into smaller sections for as a chapter or a paragraph that you want to get that information from. So it's the same concept with this chunk of text for the chatbot. So what happens is that the system breaks the chunk it breaks the document into chunks so that the AI will be able to find the specific answer that you need. Now, after that, what happens is that um, for each chunk, the AI needs to find a way to kind of like understand what the chunks means. Now, unlike humans that can understand text and statement, the chatbot actually cannot do that. But in order to find a way to, link statements together, or maybe link text or documents in such a way that the chatbot will be able to give relevant answer based on that question. So what happens is that the chunks are converted into numerical numbers called embeddings. So, but the embedding itself is like you can think of it like a coordinates on a map. So each chunk of text gets its own address based on what it is about. So two chunks that are about the same meaning, for example, like exam schedules or exam dates, they would have similar addresses because they are similar in terms of semantics, I mean the meaning. So now, once these embeddings are created, what happens is that they are stored in a vector store. So you can think of a vector store as a library having that is full of books which unique addresses. Now, you want to get a book from the library, for example, all you need to do is to find their address and get that particular book. So it's the same concept with this vector store too. Now, what happens is, let's say, for example, a user asks a question like, what is the fee for MSc AI course, or is AI course available at Ulster University? So what happens is that question itself is going to be embedded as a numerical number. So it is through that numerical number that it is then searching the vector store for similar vectors, which is, and from there we are going to have like a rank result for the result that is best ranked when it is searching that vector store. And the best ranked result will then be fed as prompt together with the context for the LLM to use. The LLM then takes that and use it to give a response back to the user. Now you can think of prompts as a way to give instructions to the LLM. Now, as I have said before, data set and chunking, uh, the data set is from the Faculty of Computing Engineering and the Built Environment at Ulster. So, and the picture, the blue, I mean, the picture here, where you have the blue, yellow, orange, and the brown. So, those ones, they represent an example of chunk, while the green one represents an overlap. Now, why do we need an overlap? So the overlap helps to preserve semantic connection across chunk boundaries. And we allow the end of each chunk to kind of like slightly overlap with the beginning of the next one. And the reason is we want to ensure that important information isn't cut off and it is preserved across chunks. So about the vector store and prompting, as I mentioned before. So the vector store houses the embedding. So it's and on this part is how an embedding might look like. So it's a numerical number that can continue for several hundred dimensions. And it is through this embedding that we are able to kind of like map each text or each statement together for whatever questions a user has, or maybe a student or a staff or whichever one. So again, the prompt too is what you're looking at on this side. So the prompt is how you give an instruction to the LLM. Like when a user has this kind of question, this is how you respond. This is how you respond. Like it's a way to control how the LLM behaves. Now, the generation is the final stage of the chatbot. So the RAG system merges the user's query with data retrieved from the FIS vector store. So FIS stands for Facebook AI Similarity Search, and it's one of the vector stores available as open source for use. And so the results from the vector store the best rank results from the vector store will be fed together with the prompt as context for LLM to use. So LLM takes that and uses it to give a response to the user. And on this side is the chatbot itself, concerning how it looked like in terms of UI. And Streamlit was used for the development. So in terms of evaluation, we tested the chatbot with 60 questions, which is generated by GSCAD. So GSCAD is a tool for generating ground truth dataset. And you can think of the ground truth dataset as a bank of question and expected answers, kind of. So, and to evaluate, we compare the chatbot generated answers against the expected answers. And the metrics used for the evaluation were cosine similarity, rigorous evaluation, and then human feedback. So the cosine similarity measures how closely related the generated and the expected answers are in terms of semantics. Rigorous on the other hand uses LLM under the hood to evaluate and compute metrics for RAG agents. So it produces a score between 0 and 1, with 0 being the worst performance and then 1 being the best performance in terms of the metrics. So, and lastly, like I said again, we used human feedback to assess the chatbot's responses and then compared it with response from the likes of ChatGPT. So, from the experiment of developing a chatbot with 3 different base models, we used GPT-4, 4 mini, and 3.5. So our discovery is that the chatbot based on GPT-4 produced the best cosine similarity score, although slightly when compared to other models. So what this means is that the response from the chatbot, the one based on GPT-4, the answers closely aligned with the expected answers from the ground truth data set. On the other side is the rigorous matrix, that's the rigorous radar. So the metrics have a score between 0.8 to 1.0, indicating that it has good performance in terms of answer and then context accuracy. And also you can see that the harmfulness, it's also has a reasonable performance in terms of minimizing harmful content. So the harmfulness here is 0 because being 0 means that that's a good number. So I did mean that it was something like close to 1 or 0.4, 0.6 thereabout, then that's going to be a poor result. So in terms of human evaluation, we tested 30 questions. Now, we thought, for example, that students will be tempted to ask ChatGPT just about any questions concerning the university. So we compared the answers generated by a RAG chatbot to the answers generated by ChatGPT on 3 base models, so which is GPT-4, 4 mini, and 3.5. So the observation is that RAG chatbot actually gave the best performance with about 90% accuracy. And on this side is the kind of question that was asked on the chatbot and compared to ChatGPT's response. So RAG is an evolving field. It's so, for example, in terms of literature, what we're able to get is limited. Then one important thing is that we tested our system on a small data set from Ulster University's website. So at the moment, we are not sure of how it's going to behave on a larger data set, but that's definitely something we are working on right now. So another important thing is that the LLMs that we used in our system, it comes with cost implication, especially GPT-4. So another important thing is that rigorous evaluation framework itself, while it was very helpful, there are ongoing debates about its reliability. So moving forward, what we plan to do is we want to develop better solutions for evaluating the chatbot memory and the chatbot history. We also want to test our system with open source LLM in order for us to see how the chatbot, in order for us to compare the performance. So then another thing is we want to explore advanced and modular approaches to RAG architecture. We want to evaluate the performance with different types of data, for example, the likes of graph or SQL. And then lastly, we want to incorporate agents in order to see how smarter the chatbot can be in terms of performance. So in the end, we managed to develop and evaluate a university chatbot using RAG approach, which has shown to be more effective than which has shown to be more effective for domain-specific information when compared to the likes of general purpose agents like ChatGPT. Also, before the likes of ChatGPT, there were chatbots that employed keyword-based solution. So, for example, the likes of Eliza, Parry. Now, the problem with this kind of chatbots is that they lack contextual awareness and they can only provide responses based on keywords matching. And this is where RAG chatbot outperform the likes of what's it called? Those kind of chatbot, the keyword-based chatbot. So lastly, the research demonstrates how we can harness AI to solve real-world problems in education, and it opens the door for future innovations for future innovations in information retrieval. While our solution was tailored for a university use case, the approach is quite adaptable to many organizations with information retrieval needs. Thank you. Thank you all for listening.